Okay, so this is where we are starting today. System response with Laplace for the mechanical system. The difference between the earlier system and this one is the order. The previous one is first order system and it is an RC circuit, whereas this one is a second order system. So we follow the same procedure here, irrespective of the system order. So if you look at the equation 2.2 earlier, right, if you don't remember that, we can pedal back quickly, right? This is the mechanical system. Is that is the one previous one? Maybe over here, right? This one. If you model the motorcycle shock absorber, right? So you get to this system model 2.2. Y is the oscillation of the seat, right, from a datum. Say this is the zero position, and the movement downward, right, is y, and the speed is y dot, and acceleration is y double dot. So when you try to model it, it automatically or naturally comes to a certain order, and in this particular case, we got to second order system, right? Y double dot plus b over m y dot k over m y 1 over mf. So immediately you can see the force, right? When you jump on the motorcycle, right? That is the input signal, right? The total weight on the motorcycle, right? It's related to the position, velocity, and acceleration in some complicated manner. Okay, so that is why we call it dynamic system. Now, if we move on to where we came from, right? That's this one. This is the equation, and to simplify the equation, right? We better introduce some symbols, right? Rather than B over M, I would say 2 sigma, and K over M is replaced rho. Okay, we introduced 2 symbols just to make life easy, and 1 over M is eta. Okay, so then our process is we want to transform the equation from time domain to Laplace domain, because this is a differential equation, second order differential equation. We say we don't like differential equations. We want to change the appearance of the equation to an algebraic equation that we like, right? So therefore, we transform from time domain to Laplace domain. So let's do that. Now, if you look at y double dot, refer to the Laplace table, double dot. This is the Laplace table. Where is double dot? Double dot comes over here, differential. D square ft over dt square, n equals 2. So when you put n equals 2, right, that is second order differentiation in time domain. In Laplace domain, it will be s to the 2 s square fs minus s to the 1, that is s f0 minus s to the 0 f dash 0. Okay, so that is the Laplace expression for the second order derivative. And it has the Laplace itself, that is fs. But in addition to that, you have f0. f0 means the 0 time 0 position. Okay, the variable at time 0 in time domain. And also f dash 0. That is the speed or the first derivative of whatever that variable in time domain. So these are time domain values of the function. You just figure that out. But at time 0, what is f dash, and bring it over here. And in Laplace representation, we don't have anything other than fs, right? We don't have f dashes or integration of s. That is the beauty of going to Laplace. Okay, so then the first term y double dot t, we will write it as s square ys minus sy0 minus y dash 0. Okay, straight from the table. Then the second term, 2 sigma times y dot t. And again, dot is the first derivative. If you pedal back to Laplace table, you will see the differential f dash t, right? First derivative. In Laplace domain, it will be sfs minus f0. N equals 1, okay? 1 minus 1 is 0, so there's nothing here, just f0. So there you can see 2 sigma times sys minus y0, okay? Then finally, rho yt becomes ys. On the right-hand side, you have eta times ft in Laplace is fs. It's very clear. Now we have transformed the entire differential equation 3.51 into Laplace domain. And now we don't have differentiation, integration. It's a simple algebraic equation. So what we do next is we simplify it, right? So you can see it over here. I have ys terms, s square ys, 2 sigma sys, and rho ys, right? I have to collect this ys, and this ys to one place like this. And after that, I have s term and the constant term. So the constant terms are like 2 sigma y0, right? And y dash 0, right, over here. So the equation will look like this if you further simplify it, so that this constant term goes to the right hand side. Then it becomes eta fs minus this thing, right, and divided by the coefficient in front of ys. So that is s square plus 2 sigma s plus rho, right? And in the next step, this goes to the right hand side. And this is how it looks like. Clear? The first term here is all y0s plus 2 sigma y0 plus y dash 0, right? So this is one term plus eta over s square plus 2 sigma s plus rho times fs, second term. The difference here is that the second term is actually coming from the external force, and the first term, right, it doesn't have anything to do with the external force. It is the system's own dynamics, okay, because of the initial conditions. Now you can see it over here, y0 is the initial position, and y dash 0 is the initial speed. Now let's say, for example, y0 is 0 and y dash 0 is 0. So the motorcycle initially was at 0 position. Okay, it's normal position and without any motion. Okay, so you might ask, isn't it the normal situation? Yes, it is, right? But there can be other situations where you jump onto a motorcycle which is not at rest, which is still in some sort of motion. So the position is not zero and speed is not zero either. So that is the more generic, inclusive type of scenario. So we better model for that scenario. So in that case, if we want to model the motorcycle shock absorber, which is at rest initially, of course we can do that. Okay. And if you want to model a shock absorber which is not at rest initially, right? This way we preserve the provision to do that, right? So if the motorcycle was at rest before you jump on it, then this is zero, this is zero, this is zero, then only you have this term. Okay, there is no initial condition solution. So this term produces some sort of dynamics, right? The moment you jump onto the motorcycle and onwards, right, the seat goes on through a certain motion, and part of that motion is coming from this initial conditions, this part. Okay, the other part is coming from your force, the force. All right. Now, if you look at 3.52, this is a milestone. This is a milestone. And from this point onwards, there are different ways we can proceed. There are different ways we can proceed. Generally, there are three different responses possible. Three different responses coming from this expression, 3.52, based on the determinant of the denominator polynomial or characteristic equation, which is given by the denominator here, right? So if you look at this denominator, s square plus 2 sigma s plus rho, it is common to both terms on the right-hand side, right? Depending on the nature of this denominator, the system response will change. That's essentially what I want to convey you. Now, if you take this denominator and set it to 0 and try to solve for s, we call the values of this s as eigenvalues, right, of the system, right? Or we call it poles of the system, eigenvalues or poles of the system, right? The eigenvalues of poles are the representative parameters of the response. The moment you know the solutions of the denominator equals 0, you can immediately understand what sort of response you're going to have, right? When you transform this back to time domain, you get yt here on the left-hand side. Yt is the time domain signal. You want to know what yt is. Whether yt is oscillatory, whether it is exponential decay, or whether it is exponential rise, or oscillatory decaying response. What is that? Okay, that the nature of that response, right, is actually indicated by the eigenvalues of the system. Eigenvalues are the solutions of the denominator, a polynomial s square plus 2 sigma s plus rho equals 0. Okay. Now, when you write that equation, s square plus 2 sigma s plus rho equals 0, We call this characteristic equation. And then the next step, you can calculate the determinant of the quadratic equation, which is 2 sigma square minus 4 1 and rho. This is b square minus 4ac. Remember, in O level, you would have done this in the parabola base sums, right? B square minus 4ac. Or any quadratic equation solving, we use that. So the determinant is actually 4 sigma square minus rho. So eventually we have got it to a very simple expression. 4 times sigma square minus rho. So let's forget about 4. Is sigma square minus rho. Now what is sigma? If you go back and figure it out over here, sigma is b over m. What is rho? Rho is k over m. So for both, the common denominator is m. So let's forget about m. M is the mass on the spring, a shock absorber. If you leave that aside, it's b versus k. B versus k. Right? It's b versus k. This is basically b. This is basically k. So if b is bigger than k, or k is bigger than b, or they are both equal, you are going to have different solutions, different responses rather. Okay, different responses. So b is the damper. B is the damper. You can have a strong damper or a weak damper. And rho is actually k. K means a spring. You can have a strong spring or a weak spring. Now you can see, right? You can, if you want to design a shock absorber, you have to purchase separately, right? A damper and a spring. Damper and a spring. So you might, without knowing what is what, right? You would probably purchase a strong damper and a weak spring, or a weak damper and a strong spring. Sometimes you might hit a nice balance, right? So depending on what you choose, you're going to get different responses, I remember a very nice story. A long time ago, I used to go to these wildlife trips with Dr. Amit Munindadasa, late Dr. Amit Munindadasa. And he had a Land Rover. He is the one who repairs it himself. And one day, I figured out that when we were in, I think it was Amparo somewhere, right? If the Land Rover, every time it goes over a small rock or a little pit on the road, this keeps on oscillating for another couple of minutes, right? It doesn't just damp out, right? So the reason is Dr. Muninder Dasa has replaced the shock absorber, right, of the vehicle, and I don't know what he has put. Either I think it's a leaf or coil spring. I think it's leaf, right? If he didn't put the right one there, he might have simply given it oscillator response, right? Simple as that. So the poles are different, eigenvalues are different. Now this is not the original design anymore. So the system does not damp the vibrations. So it was very, very uncomfortable for the people who were sitting in the back, right, of the Land Rover. It was very, very uncomfortable ride. So now if you look at modern vehicles, motorcycles and other vehicles, that's somewhat comfortable, right? When you drive, all the irregularities on the road roads are not flat, right? But you don't feel that profile, irregular profile, right? Because of the shock absorber. It will damp all these vibrations, right? Irregularities are actually damped, absorbed by the shock absorber. If the shock absorber has to provide additional length, it gives that length. Or if it has to squeeze some amount to reduce the length, it does that. So therefore, it is adjustable height adjuster. It's basically a height adjusting mechanism, right? It adjusts your height, right, to keep it at a constant level. Even though you are actually going through very irregular line on the road, right? So that is the purpose of having a shock absorber. Now, in this case, for shock absorbers, you definitely do not want oscillator response, because if it's going to oscillate, it's very uncomfortable, right? And also you don't want very hard thing, right? Because every time you go on a piece of rock or something, it's a huge impact, right, on you, and it's again very uncomfortable. You don't want it to be like a piece of rock, solid. Okay, you want the shock absorber to squeeze, but gently. Okay, not a oscillation, but it's a simple damping behavior that you want. Right. So let's look at the first case where sigma square is greater than rho. So there you can see the combination. The determinant of the quadratic equation, right, is 4 times sigma square minus rho. So if the determinant is positive, you have two real roots here for this quadratic equation. Two real roots. You know that, right? Any quadratic equation, if the determinant is positive, you have two different real roots. That is case number one. Case number two, let me just pick up anything as to if the determinant is zero, then this equation is going to have two coincident real roots. The two roots are on top of each other and they're both real, but they're coincident, right? They're on top of each other. Then you get a different response. And the third case is where the determinant is negative. So that is sigma square is less than rho. In that case, the characteristic equation is going to have a pair of complex conjugate poles. The poles for the eigenvalues are not real anymore, but they're complex. And the beauty is that these two eigenvalues, they form as a pair of conjugate poles, which means they are not just random poles. If you look at, this is the imaginary axis, the real axis. Conjugate pair is like this over here. The other one is over here. So they have the same real part, and the imaginary part is same in magnitude but different in sign. Okay, so if you look at this one as rho, so let me call it like say, if this is A and if this is B, this is just minus B, that's it. And this is the J-axis. So the two poles are, one is A plus JB, the other one is A minus JB. So that is what you call conjugate pair, right? You know that. So let's take the first case, right? Where sigma square is greater than rho, or in other words, sigma square minus rho is positive. So then if you substitute for sigma, which is what? Sigma is b over m, right? B over 2m if you want. And rho is k over m, right? If you substitute these two over here, you get the inequality as b is greater than 2 times square root mk. Right? So what does it mean? This is a situation where you have a strong damper. You purchased a strong damper compared with the strength of the spring. So you have a spring. Spring is basically oscillation, right? Now oscillation behavior is kind of weak, and damping behavior is strong. So please try to understand the physics, right? Through the mathematics, try to always understand what's happening in the physical world. This is the situation where you have a strong damper. Damper means it doesn't allow you to move. It's like friction. It resists the motion this way or that way, right? And K is the spring, right? Spring is now weak. Spring is weak. So spring means oscillation. The moment you think about a spring, what comes to your mind is oscillation. So this is a situation where you don't get oscillations, but system is very slow because of the high friction. This is like a very high friction damped system. So therefore motions are not easily possible. Okay. So before we even go for mathematical derivations, we can understand what is to be expected. Okay. So that approach is extremely important for a rational person, and particularly for engineers. Okay. Right. So the next step, what we do is we write the equation 3.52, right? This equation. This is also a bit too ugly. There are a lot of things here. Why don't we introduce some parameters? Say K1 is plus K2, and K1 is this one. K2 is this one, right? We are simply substituting K1 for Y0 and K2 for this whole thing. So both K1 and K2 are initial conditions, right? The level of the motorcycle seat and the speed of the motorcycle seat at time 0. So they are K1 and K2. And the denominator, this one, you can write as two terms, S minus alpha 1, S minus alpha 2. Now these alpha 1 and alpha 2 are eigenvalues of the quadratic equation, okay? Eigenvalues or closed loop poles. Don't have to worry about closed loop or open loop here, just say poles, right, for the moment. And the other thing I want to mention here is that this Fs, this is the forcing function, external forcing function. We have to pick up a forcing function for this one. So why don't we try to see the real world? So you have, say, 50 kilograms, you're a 50 kilogram person, and you jump on the seat. So it's like a step input to the plant with 500 Newton force. So you can put it like that, A over S. A is 500. This S means, 1 over S means step response, right? If you go back to Laplace domain, you can see 1 over S is equal to ut. Ut is the step signal. ut is step signal. You know that, right? Ut is something like this. So this is 1. Okay, all right. So the two eigenvalues alpha 1 and alpha 2 are given by this minus sigma plus or minus square root sigma square minus rho. So where do I get it from? I'm getting it from the characteristic equation here. Sigma square minus 2 rho is plus rho equals 0. They are alpha 1 and alpha 2. These are solutions for the quadratic equation are given by minus 2 sigma plus or minus this thing square, right? Minus 4 rho divided by 2. You know how to solve a quadratic equation. I don't want to spend time over here. When you do that, this is your answer. Alpha 1 and alpha 2 are given by this. Now, because sigma square minus rho is positive, this is a positive number. So you have a real root here, square root, right? So minus sigma plus or minus a positive number. Okay. So you get two poles which are real and distinct. Real and distinct. So if I draw it over here, this is a real imaginary axis. So over here, you have sigma, right? So one of your poles are here. One of your poles are here. Okay. So two poles are like that. Because you add a certain quantity to minus sigma, and then you deduct the same amount from minus sigma. So you go same distance from here to your left and to your right, and these are the two locations. So in this particular case, if you have a strong damper and a weak spring, your characteristic equation is going to have two distinct real poles. And if you know the damper coefficient and spring constant, you can numerically calculate the pole locations. Okay. Now let's solve this. To solve the Laplace equation 3.52 over here, let's use partial fraction first, right? So then you can write it down as 4 terms, right? 2 over here, and actually 3 terms, 3 over here, because 1 over is another term. So you have P1 over is minus alpha 1, P2 over is minus alpha 2, 2 terms coming from the first term, and then the second term will produce 3 terms. Again, I'm not going to discuss partial fraction expansion. There's enough documents on the internet. If you have forgotten, you can self-study that one. So this is a graduate level course, so we cannot go back to fundamentals very often, right? And if you use the cover-up method, there's a method called cover-up method connected to partial fraction expansion to figure out the coefficients. So if you do that, you can say P1 is given by this, P2 is given by this, Q1, Q2, Q3 are all given by this. Okay. Right. So now if you look at P1 and P2, what's in there? You have K1, K2, alpha 1, alpha 2. Alphas are actually coming from sigma and rho. And sigma is coming from the damper, rho is coming from the spring. So these are actually spring and damper dependent numbers, okay? And then K1 and K2 are initial conditions. the initial position of the shock absorber and initial velocity of the shock absorber, right? So P1 and P2 are like that. They have nothing to do with the force on the shock absorber. Your weight and all has nothing to do here in the first two terms. And if you go to the other three terms, Q1, Q2, and Q3, they're like this. They don't have initial conditions like K1, K2, right? Initially, where the seat was, whether it was moving or not. No, there's no talk about it, right? They're basically alpha 1 and alpha 2. So which means damper and the spring. So depending on what sort of a damper you have, what sort of a spring you have in the system, you have already decided what Q1, Q2, Q3 are, right? But they appear together with A. What is A? A is the mass or the force on the shock absorber. So therefore, they are connected with the external force. External force and the system components. Here, the first two terms, they are connected to system components and the initial conditions. So this is a very interesting representation. If you wish, the first two terms, or all the terms, first two and the second three, right? They're all system parameter dependent. That is the damper and the spring. They are there in everywhere. They are the system components. Your damper, your spring, they have to be part of every term here. Okay? You can't have a response without the system parameters. Now here, the first two terms, in addition to the system parameters, you have the initial position and velocity, but you don't have external force here. But if you go to the next three, you have the external force connection, but no initial conditions. Okay, so the five terms in two groups, they're very specific in nature. Now, if you want to get back to time domain, you need to transform the equation, this one. Now you can forget about these expressions for P1, P2, Q1, Q2, Q3. Just look at this one. Every term you can transform back to time domain, because say this is P1 over S minus alpha 1. What is the inverse Laplace? You can go back to the table. If you see anything similar to that, it's like this 1 over S minus A. The time domain is e to the at. Okay, A is the pole here, S minus A. So this one, S minus alpha 1, in the time domain, it will be e to the alpha 1t, e to the alpha 1t. So that's what you have here, e to the alpha 1t. And the second term, S minus alpha 2 in the denominator. So in the inverse Laplace, that is in the time domain, it is e to the alpha 1t. E to the alpha 2t. And all the other terms are like that. This is e to the alpha 1t, this is e to the alpha 2t, this is 1 over s, and 1 over s is different, right? 1 over s is a step signal, ut, right? So we just write ut here. You don't see ut here, but it is one step signal. So now you have e to the alpha 1t in multiple places, right? And e to the alpha 2 in multiple places. You combine them together with a constant. E to the alpha 1t over here, e to the alpha 2t over here, and eta a q3 is over here. Now, alpha 1, what is alpha 1? Alpha 1 is a negative number, negative real number. What is alpha 2? Alpha 2 is also a negative real number. over here. They are both negative real numbers. This is alpha 1, this is alpha 2. So if you see e to the alpha 1t, which is where alpha 1 is a negative number, this is going to die over time. So is this one. So both these responses, the last two terms in 3.56, they are not going to show any non-zero residual response in the long run. Okay, and they are going to decay sooner or later. So we call it transient response. They only last for a while. So in the long behold, what remains to be seen is only this part, steady state response. We call it steady state because it's gonna be there forever. So initially you can see some sort of oscillation, not basically oscillation, some change in the response, and it will eventually settle over here, this value. Okay. So now, did you get some sense of how you use Laplace transform to bring differential equations into the Laplace domain as algebraic equations, and then do the partial fractioning there and break it down to small blocks so that each one you know in the Laplace domain, and you can bring it back to time domain. Then you know what these time functions are, right? So rather than solving and getting to the final response, our major requirement here is to learn, right? How to analyze these systems, to develop more intuition, knowledge about how the systems work, right? And we often say the response coming out of a system is actually the interaction between the input signal and the system. As a result of that, you get the response. This interaction is mathematically known as convolution. Okay, so let's look at the convolution approach in generating the response. So if I start with 3.55 rather, right, this is that equation, as you remember that, right? I'm picking up from here, right? Somewhere here, 3.55, yes. And then first two terms, I don't have to do anything because they're partially factored already. But this one, I'm going to write it like this. So it is eta times P3 Fs over S minus alpha 1, then P4 Fs S minus alpha 2. And in these two terms, last two terms, you can see two Laplace transforms, right? Say this is one Laplace transform. This is another one. So this is the product of two Laplace transforms. Say if I write one as G, the other one, this is multiplied by H. Two Laplace transforms. So this is what is called the convolution. Multiplication of two Laplace transforms. So in the time domain, right? In the time domain, this is Laplace, but if you go to the time domain using inverse Laplace, right? This is the integration. Oops. Right? Integration. You get one of these functions like G, time domain G, right? T minus tau. The other one is h tau d tau, right? From 0 to t. So this is how the signal and the system interacts. The system and signal interacts. You can take this as a signal, this is a system, or even if you interchange, doesn't really matter, right? In Laplace domain, it is a complicated mathematical function, okay? But in Laplace domain, it's just a multiplication of the two Laplace transforms. So the convolution is happening based on the time function. The multiplication is between the Laplace transforms, okay? Right. So this is how we implement the convolution integral thing. Maybe a bit complicated, but you have to go through this process, okay? Otherwise, it's not complete. Your learning curve is not complete if you cannot handle a convolution integral, okay? So there's no other way, right? You have to just take it up. So the first two terms, we don't worry too much. We just write them as it is. In time domain, it is e to the alpha 1t, e to the alpha 2t, right? The other two terms are convolution integrals, right? Convolution integrals. So the first one, if you look at e to the alpha 1t minus tau, it is coming from, say, let me erase some of these scribbles. Right. So let me take this part here, right, as one of the functions, and I know that in time domain this is equal to e to the e to the alpha 1t, e to the alpha 1t, right? So I bring it over here and I write e to the alpha t minus tau, okay? So that's what I'm doing here, e to the alpha 1 t minus tau. The other one is fs, so I just write it as ft. In this particular case, the integration is with respect to tau, not t. So it is f tau d tau. Okay. And the final term is eta p4 integration 0 to t e to the alpha 2t minus tau f tau d tau. Now you have to integrate this one. For a known function ft, ft is AUST. A is the weight of the person and the seat, everything. And at time 0, you exert that force on the shock absorber. And for the rest of the time, it's going to be there. So it's a step signal. Again, first two terms are already done. Third term, eta p3 integration 0 to t e to the alpha 1t minus tau. This becomes, ft becomes a d tau, right? A d tau. UST is 1. The fourth term is also the same, eta p4 integration 0 to t e to the alpha 2t minus tau a d tau. Let's do the integration, right? E to the minus alpha 1 tau, you keep it there because that is the subject of integration tau. T is a constant with respect to the integration. Okay, so therefore e to the alpha 1t comes out of the integration. T is only in the limit of the integration. It's not the subject variable of the integration. So it is e to the alpha 1 tau a d tau. You can take a also out. Same thing over here. So when you do that, a, eta, p3, e to the alpha 1t, they're all constants divided by alpha 1. And then integration over here is e to the alpha 1 tau. divided by alpha 1 that comes over here, integration 0 to t. Simple integration, and eventually you get to this equation, right? So you get the notes here. You can study again. I recommend you do that at home, line by line, right? Expression by expression, you have to work it out. Manually do that yourself until you get the full confidence, right? Now, when you get to the final stage, right, if you look at what you have minus eta A, P3 over alpha 1, P4 over alpha 2. What is P3, P4? P3, P4 are constants. P3, P4 are constants and depends on alpha 1 and alpha 2. Alpha 1 and alpha 2 depends on the damper and the spring or system components, right? Don't forget that. So this is something that depends totally on system components and A. A is the total weight on the shock absorber, the external force. And this is independent of time. It's going to be there. So it is the steady state response. And if you look at the transient part, you have P1, P3, eta, A, and alpha 1. They're all system component dependent, right? System components. And in addition to that, you have e to the alpha 1t. Alpha 1 is a negative number. So therefore, with time, this part is going to die. Exponential decay. So is here. This part is also an exponential decay, right? So this is the same thing you got earlier also. Here, constant term and 2 exponential decays. Okay. So either you just stick to the partial fraction expansion method or partial fraction with convolution integral. Either way, you get to the same or similar expression, but when you simulate it, you will see exactly the same thing. So what is the comment here? We see the transient response, it decaying, right? It's a decaying function. And it depends both on initial conditions and external forcing function. You can see e to the alpha 1t, e to the alpha 2t. These are the transient responses. If you look at inside, you have system components as well as A. A is the external forcing function. And you can see the steady state response is the first term, eta A, P3 over alpha 1, P4 alpha 2. So this is independent of the initial conditions, right? It depends on the system components and the external force. So it's not complete if you do not simulate this one also, right? How to do that? So let's define the system parameters. What do we have? We have the spring. We have a spring, and let's put a number for the spring constant. I would say 125 newtons per centimeter. So every 1 centimeter that you squeeze, you have to deliver 125 newton. Or in other words, let's say it's a 12 kilograms something. So you put 12 kilograms on the spring and you get only 1 centimeter squeeze, okay? And you have a shock absorber, you have the damper, 700 Newton per centimeter per second. So what does that mean? It means if you want to resist a motion of 1 centimeter per second, right? If you are trying to move it with 1 centimeter a second speed, the damper will resist you by opposing with a 700 Newton force. It gives you 700 Newton opposing force, so nearly 70 kilograms, right? If you try to move it by 1 centimeter every second. So that is quite a lot, right? That's quite a lot. So this is the first case where damper is very strong compared with the spring. And let's say M is 50 kilograms, okay? So with these numbers, if you revert to equation 3.51, where is that? 3.51 is the system dynamics. There you can calculate system parameters, even close to poles, right? Sigma is 7, rho is 2.5, and eta is 0.02. The two system poles are alpha 1 at minus 0.181 and alpha 2 is minus 13.819. So the moment you know the system components, there's a spring and the damper, you can calculate the eigenvalues of the plant or the poles of the system dynamic model. And they're both real and distinct, okay? Real and distinct poles. Let's look at the MATLAB code here. So you can see the code here, duration 25 seconds, mass is 50, B is 700, K is 125. These are the other possible cases, case 2 and 3, right? And I calculate my sigma. Sigma is B over 2M, rho is KOM, eta is 1OM. And the D is sigma square minus rho, that is from the determinant. A is 10 times M, the force, right? And this is my time scale for my simulation. I start with time 0 and go up to the duration, whatever it is. There you can see duration is 25 seconds in this case. And I sample the time scale with 0.01, that is about 10 milliseconds, right? Every 10 milliseconds, I calculate the response. Here I put some initial conditions, y0 equals minus 1.5. So when you begin the experiment, or when you jump onto the seat, it was not at rest. It was actually minus 1.5 centimeter level, which means above the 0 level by 1.5 centimeters. And also there was a speed 1.8, right, centimeters per second. So it is a positive speed, which means downward speed. Then my system coefficients K1, K2, I can calculate. There you can see alpha 1, alpha 2, P1, P2, Q1, Q2, Q3, Q4, right? And YH, YE. YH is the homogeneous response. This is because the response due to the initial conditions. And YE is the response due to the external forcing function. Right, only that part. And if you continue, you can see P4, P5, YH, YE for the other ones, right? So because I said you there are 3 possibilities. So this code takes care of all 3 possibilities. in the runtime, right? While it is running, it decides whether it is case 1, case 2, or case 3. Whatever it is, whatever the case may be, eventually, once it completes calculations, you have total response is equal to YH times YE. And then what follows is plotting. You plot the graphs. So this is the first case where damper is stronger than the spring. So we call it overdamped response. Overdamped response. Okay. Damper is stronger than the spring. So this is the homogeneous response. As you know, initially the seat was at minus 1.5 centimeters. So over here, minus 1.5, right, initially. So after that, it goes to 0, nearly 0. And then exogenous response, initially there was nothing because there was no force initially. So therefore, there's no deflection due to the external force initially. But after that, there's a force. So the seat has to squeeze to some depth, positive depth, right? So this is the exogenous response and this is the total response. Now, again, as we did in the previous case, can we verify that what we see on screen is probably correct? Any rational way to verify this result? Anybody? Right. So let me help you. Right. So this is the system we are dealing with. We have 50 kilogram person over here. 50 kilogram person over here. So total force is 500 Newton. So you have a spring and a damper to resist this 500 Newton. If you look at the equations, how they produce the forces, you can clearly see their characteristics. Spring produces a force proportional to the deflection, how much the spring squeezes, or the deflection of the mass vertically downward. Damper produces a response based on the velocity. It's not the position-dependent force, it's a velocity-dependent force. Velocity. If there's a velocity vertically downward, it produces a force. And the moment there's no velocity, there's no force from the damper. Okay? So if you see this motorcycle with whatever huge load on top, when you stabilize the whole thing, You can remove the damper and nothing will happen. Damper is not taking any load when the system has no motion. When the motions are settled down, when the velocity is zero, damper is just sitting there. It is elongated, the length is different, but it can stay there without producing any force. It produces the force only when it is moving. Only when it is moving. It can stay at this level or this level or that level without producing any force. The moment you try to move it up or down, then it produces a force. See the equation, y dot. Y dot. Spring is different. Spring produces a force wherever it is. If it is not at rest, there's only one position, that is zero position for the spring, not to produce any force, but any other position, up or down, it produces a force because the force is coming from the deflection. Now you can tell me what's going to happen here. So after settling down, there's no motion, there's no velocity. Therefore, damper is not producing any force. Take the damper out, and it is a 500 Newton force balanced by the spring. Look at the spring constant. Spring constant is 125 Newtons per centimeter. So every 1 centimeter squeeze gets the spring to produce 125 Newton. So if you look at the total weight, 500 Newton, how many centimeters to squeeze? How many centimeters the spring has to squeeze to produce 500 Newton?
4 centimeters.
4 centimeters. Then check whether we have got 4. Yes, we have. Exogenous response, 4 centimeters. So this is the point where everything is settled down. No velocities anymore. Zero velocities. Okay. Everything is settled down. Spring squeezes to 4 centimeters. So this is how you give some physical meaning to what you see, right? This is one of the problems in the engineers nowadays. Right? They don't verify their outcome results with the physical world. That verification is extremely important and it'll make you a competent engineer, right? Any questions about this? Right. So let's take a little break here and I'll see you in about 10 minutes, right? Okay. Welcome back. Let's look at what other possibilities are there for the response. Okay. Certainly, you know that when you have a spring, right, you could also get to some sort of oscillator response, right, going up and down, not like this. So you got this particular response because you had a very strong damper. Damper does not allow the oscillations to take place. It doesn't allow any motion to happen. Okay, and oscillation is one of the types of motions. So it doesn't allow anything. But if you weaken the damper, which means you let some motions to happen, then you will see the spring action. So that is a different type of response, right? You cannot get to that response unless you change the system components. Here you have two components, spring and the damper, right? So now let's change it to the second case where sigma square is equal to rho, right? In that case, is a very delicate balance between the spring and the damper. Mathematically, it is B equals 2 square root of mk. So for every k, there is a particular B and vice versa. If you do this math and purchase the damper and the spring, you are in case 2. You are in case 2. So here, what we can understand is that you could believe that you have comparable components, spring and the damper. Please understand that you cannot compare a damper with a spring, right? Like you cannot compare apples and oranges. Okay, they're different. Here, I'm trying to explain a situation where spring action and the damper action are in some sort of comparable state. Okay. So then equation 3.52, if you look at that one, where is 3.52? Let's get to that one. Over here, this equation. So if I move it a little further to this one, right, to this one, you are in a situation where both these alphas, alpha 1 and alpha 2, they are same. You don't have two distinct poles, but the two poles are on top of each other. Okay. So you can write now your system response as K1S plus K2 over S minus alpha square, because the poles are coincident. And the second term also will look like this with the external forcing function Fs. So moving forward, we can fraction this first term, say for example, into two terms like this. Now the two terms are different here because when you have the repeated poles, when you do the partial fractioning, this is how you do that. You get S minus alpha whole thing square in one term, and the other one S minus alpha. Okay, this is how you do the partial fractioning when you have multiple poles or repeating poles, right? And same thing over here. So P5 and P6, you can get it from the cover-up method, and they are like this and entirely based on the initial conditions and the system components like B and K, and initial conditions are y0 and y-0, the initial position and initial velocity. Okay. So now it's up to us to do the Laplace transforms and see how we can solve this. So if we take the first route, which is what you see over here, right? You have P5 term, P6 term, P7 term, P8 term, and then just a side of that, A times 1 over S. This is the external forcing function, okay? These two terms, you can take them as isolated terms, and there's a positive sign here, right? Plus over here. Sorry, it is missing. We have to write it down, plus over here. And then A times 1 over S, you can take into these two terms, P7 term and P8 term, and you can write it like that. Now, if you stick with me in this process very carefully, very closely, you will learn a lot here, right? The whole expression is ys. That is the response. But that is in Laplace. We don't understand Laplace expressions. It's a very complicated domain. We want to transfer it back to time domain. This is exactly what we are doing here. And we have 4 terms. We have to inverse transform all 4 terms. Okay. I would start with the simplest one, which is over here, P6 term. Because I know this term. I have dealt with this term earlier. P6 over S minus alpha. Okay. If I go back to the Laplace table, I can see this term right in the Laplace table. And to the left of that is the time function, which is e to the alpha t. Very simple. So I inversely transform this one into the time domain, and it will be P6 e to the alpha t. All right, so there you can see that term, P6 e to the alpha t. What I do next? I can go to the next term over here, third term, P7 term. And also I can see that there's a relationship between P6 term and P7 term. Right? P7 term is actually the differentiation of the P6 term, this one. You do your math later, differentiate P6 term, this one, 1 over S minus alpha, with respect to S. In Laplace domain, you can differentiate with respect to S, okay? Very much like you differentiate in time domain with respect to time. So then you get P7 term, this one, 1 over S minus alpha whole thing square, with some other sign changes and everything, right? But that's we can deal with that later. So generally, when you differentiate P6 term with respect to S, you get P7 term. And P6 term, this is the time function, inverse Laplace. If you know a function and its inverse Laplace, do you know the inverse Laplace of the same function if you differentiate it in Laplace domain? Yes, we know. Yes, we know. Go to the table and see. In the table, you can see this one. It's not this differentiation, okay? It's confusing. This differentiation is in time domain. This differentiation is in Laplace domain. So right now we are having a situation similar to this one, the differentiation in time domain. Laplace domain. So then the time function should be time multiplication. Just put a t in front of the time function. Okay, so you don't have to worry about the differentiation over here. Don't worry about the differentiation. Look at the inverse Laplace of the function before differentiation. Right? This fs is before differentiation. Take the function, understand the function, identify the function before differentiation, and look at the time function of that or inverse Laplace of that and put in front of that simple t, time. So this is the inverse Laplace of a function which is differentiated in Laplace domain. And there's a negative sign. So if you don't have a negative sign, you have to put it over here. Right? We are over here. Our function is this one in Laplace domain. In time domain, it is e to the alpha t. So we take it over here, e to the alpha t, but we multiply with time. Simple as that. Now, how easy is that? So what does it take for you to develop this skill? I think what you need is some sort of arrangement mentally, right? Have two sides, time and Laplace, and then you see the differentiation going on in time, in Laplace, and in inversely speaking, from Laplace to time, right? You get the time multiplicated function, okay, as the inverse Laplace of a differential in Laplace domain. So if you are not confused, if you have your calm and cool in your mind, you can handle this. Okay, you can handle this. So that's the third term here. So you can see over here t e to the alpha t. This t appeared because of the differentiation in Laplace term. What else? If you look at the third one, last term here, again I can see some relationship between the second term and the last term over here. The second term is 1 over s minus alpha. The last term is 1 over s minus alpha, but there's another s here. So this tells me this 1 over s or s in the denominator is actually the integration in time domain. Integration in time domain. So therefore, the inverse Laplace of this whole thing is the integration of the inverse Laplace of 1 over s minus alpha in time domain, right? So what is that? 1 over s minus alpha is e to the alpha t, and you have to integrate it. E to the alpha t integrated in time domain. This s means integration. So once you integrate, you get this expression. Now see how beautiful this whole thing is. You have a solution for every case, every expression, right? And the first term we haven't taken into account yet. What is that? S over s minus alpha whole thing square. So I think this is related to third term here, 1 over s minus alpha square. The only difference is there's another s here. So the third term becomes the first term if you multiply by s. So S multiplication by S in Laplace domain, right, is what? Let's go back to Laplace table. Multiplication by S. Can you see over here? Multiplication by S. I think that's over here. There's no other place. S times Fs is the differentiation in time domain. So you have to differentiate the function without S, right, in time domain. So here you are, you differentiate. But as you know, when you differentiate, okay, let me go back to the table to explain that point to you. Right. So if you differentiate a function in time domain, okay, what happens in the Laplace domain is that you have this whole expression. So the first term is s to the n fs, second term is like this, and so on. If you set n equals 1, which is the first derivative, on the right-hand side, which means in the Laplace domain, you have s times fs minus f0. There you are. This initial condition minus initial condition is a constant. It has to be there in the Laplace domain. If you want to say this is equal to first derivative of ft. But unfortunately, what we have right now is only the first term here. That is s times fs. S times fs. We don't have this constant. But if you don't have this constant, what you have to do is you have to add this constant over here, the time function. Okay. So that's exactly what we are doing here. We do the differentiation and add to that the initial condition. What is the function? That is t e to the alpha t. And we set time equals 0. And this is the initial condition. We add it to the differentiation of t e to the alpha t with respect to time. Okay, and this t e to the alpha t is coming from here, the third term. The inverse Laplace of the third term is t e to the alpha t. So this is a very, very nice slide. One of my most favorite slides, because it lets the students understand how you deal with the Laplace transform table, and it tells you the differentiation, integration, time multiplication, many Laplace operations in one slide. So now, now we have the 4 time functions, right, for the 4 terms in Laplace domain, and we just need to add them together like this: P5 term, P6 term, P7 term, P8 term, and this is the result. Let's simulate this one. So this is a very peculiar design where we don't have the free choice to select the damper and the spring. The moment you select a damper, there's a specific spring and vice versa. So if you look at the earlier values, for K is 125 Newton per centimeter and B 700 Newton per centimeter per second. Now, if you just keep your damper and change the spring, you have to change the spring to a new value like 2450 Newtons per centimeter. So this is a strong spring. Now see, earlier the spring was kind of weak. Now it is much stronger, right? And you satisfy the condition that if you have this damper and the spring, you force the 2 poles, right, to fall on top of each other, right? So in that case, if you look at the alpha 1 and alpha 2, now they are coincident. You are at -7. You are at -7. So where were you earlier? Earlier it was -0.1 and -13. -0.1 and -13. Right? If I draw the S-plane, this is my S-plane, right? S-plane. Earlier I was at 0.2. This is 0.2. And over here maybe 13 -13, like that. One of my poles was here and the other one was here. But now I changed my spring to a stronger one. Now I'm right in the middle, somewhere over here, -7. Now I have two poles over here. Okay. This is the result. So I use the same code for case 2. You can see the timeline is the same as what I have earlier. My time scale, 25 seconds, still there. But you can see now, whatever happens, it has happened within the first few seconds. Like 2 seconds. In 2 seconds, everything is over. This is a very different system than what you had earlier. This is earlier. Right? It takes about 20 seconds or little more than that to complete whatever dynamics. It takes very long. But now, in about 2 seconds, everything is over. Right? So these are our observations. System is critically damped. This is the word we use for this kind of situation where the two poles are on top of each other. The system is critically damped. Fast response. Oh yeah, if you look at that, this is very fast. No overshoots. Yes, there's no overshoot. It goes like one single motion rise to a certain level and stay there. And also, if you might not know now, but you can take my word for granted, that is, this is the most energy efficient way for the system to get from one state to another. Say the first state is the free state or initial state, and the final state is you settle down at some velocity, some position with 0 velocity. Okay, so remember what was the initial condition? Initial condition was -1.5 and +1.8, if I remember correctly, right? So this is the initial condition. Y0, Y-0. Now the final condition is there's some value over here. We have to figure that out, right? Let me call it as X. The velocity is, of course, 0, right? To get from initial state to the final state, right? There's some energy you have to provide. Some energy you have to provide, right? E. And there's some time it takes, T. Right? In control theory, these are important things to know. And sometimes we design systems in order to minimize energy, right? Minimize energy or minimize time. right? There are certain criteria to satisfy. With the controller design, you design to meet a certain condition, a certain performance. If you critically damp, right, you get the minimum energy. You get the minimum energy condition. So therefore, there are a lot of control systems where you are supposed to critically damp the poles, and you do a lot of things to bring the poles together. If you have two poles, you have to bring both poles to one place. If you have 5, 6 poles, look at the most dominant poles, 2 poles, and bring them together, right? So again, if I draw my poles like this, right? So if you have a lot of poles, let's say there's a pole over here, and there's another pole over here, and a lot of poles. You can actually forget these poles because their response is not very visible. They're very fast poles, right? They are not dominant. The dominant poles are the ones very close to the origin, these ones. So if you want to bring these poles together, right, in the one place wherever it is, right, you can say your system is more energy efficient. Okay, right. And also the time. So this is a very small time. Time is another reason why energy is minimum, right? If you keep going for a long period to finish a job, you anyway spend a lot of energy there because you spend more time in there. Time means energy, right? So to reduce the energy, one way is to do it quickly, reduce the time also. Okay, that is one thing. But now, if you look at what we really want in a shock absorber, motorcycle shock absorber, do we really need minimum energy or minimum time or maximum time, or what do we need? I don't think we are really into minimum energy or energy optimization. And I don't think we are into minimum time either, right? I think what we want is some sort of comfortable dynamics, comfortable, right? So therefore, looking at the application, you have to set your criteria, design criteria. So that's another very important uh, guideline. Okay, remember that. Now, can you verify whether what we see is correct? Can somebody figure that out, please? Do you think what we see here is correct? How much does the shock absorber squeeze in this situation?
0.2 centimeters.
Yes, it's over here, 0.2 centimeters. Because 500 Newton is the total force on the shock absorber. And eventually, when everything is settled down, right, the spring has to take this entire force, right, by squeezing it, by generating 500 Newton. So for every centimeter, right, it produces 2,450 Newton. But now you have only 500 Newton, which means the spring has to squeeze only 0.2 centimeter. That is about 2 millimeters. About 2 millimeters. Then you come over here and check that out. This is about 2 millimeters. This is 2 centimeters, and this is about 2 millimeters, right? So I think it's very obvious that you don't want this kind of shock absorber, right? When you jump on it, it only squeezes 2 millimeters. So it looks like you jumped on a piece of rock. It doesn't move. Okay. So you want the shock absorber to move initially, right? Otherwise, it will be really painful experience, right? But this oscillation should not last long. In few seconds, it has to decay. Okay, so that is the kind of performance you need here. So the first one, this response, right? It squeezes about 4 centimeters. That's, I think, a bit too much, and it doesn't have any oscillation. It takes about 20 seconds to complete. Do you agree with that? Is this a good design for a shock absorber? It takes too long and it squeezes too much. Therefore, I don't agree with this kind of design for a shock absorber. What about this one? Again, I don't agree with this one either, because it doesn't squeeze at all, right? And it looks like the whole shock absorber, the seat, is like a wooden table, right? No motion at all. Let's look at, if you compare the first two options, right, case 1 and case 2, in contrast, we can have the homogeneous response, exogenous response, and the total response like this, right? This is what happens when you change the components of a plant. This can be component change in a vehicle, component change in a machine. It's not as simple as you think, right? You change the characteristic equation of the plant, the poles of the plant, right? The eigenvalues. And you're not going to get the same response or the desired response. So every time you change something, you replace a part, make sure you replace it with the right part, the equivalent part, right? I think this is common practice in engineering. Wherever you go, right, you look for that particular component, right, to replace. You don't just play with whatever you have, right? Because it simply doesn't work. Let's look at case 3. So this is going to be really interesting if you keep engaged, okay? Oh, I think time is out for today. No, we have another half an hour, right? Case 3 is when sigma square minus rho is less than 0, right? Which means B is less than 2 square root km. So which means the damper is weak and spring action is dominant. Spring action means the oscillation. Now you would probably see the oscillation for the first time in the shock absorber design, okay? And in this situation, if you look at the characteristic equation, S square plus 2 sigma S plus eta, right? That equals 0. That quadratic equation has 2 roots, and they are a pair of complex conjugate poles. So you can write them as minus sigma plus or minus j omega. Okay. So you have complex poles for the first time. So you can write down your response as like in 3.52 only the denominator is going to change. Denominator is going to get one of these poles here, the other one is there. So S minus sigma minus j omega, S plus sigma plus j omega. Okay, the two poles, they are complex poles. So you can write this one as S plus sigma whole thing square plus j omega square. So when you write j omega whole thing square, this becomes plus omega square. Okay. Same is true about here. All right. So then if you take this term over here, S over S plus sigma whole thing square plus omega square, all right. Only the first term over here, right? Only this term over here, right? You can write it like this. Right? If you look at the terms over here, you can see this omega cancel out with this omega. And when you add them together, this sigma cancel out with this sigma, you're leaving S here. So it's the same thing, okay? But the way you write it over here helps you in your inverse transformation. And the second term is over here, right? We also want to change it a little bit. Right? When you write it, the second term, right? Like over here. Again, you can see the W and W cancel out, eventually leaving just one over here, right? This is for the sake of keeping it more aligned with the inverse Laplace. Okay, right. So the third term, 1 over S plus sigma square plus omega square, A over S. There also you can see this omega appearing in the numerator and the denominator. So once you cancel it out, it's similar to this term over here. Okay, right. So why we write it this way is to make it more aligned, as I said, with the inverse Laplace transform. So we have to look at the first term over here, whether we can see something in the Laplace table, like S plus sigma over S plus sigma square plus omega square. Do we see something like that in the Laplace table? So let's go and see. Remember the pattern, S plus sigma, right? S plus sigma and then omega. Now, to help you a bit, you can see it over here. S plus sigma is appearing here and here. So this is replacement of S with S plus sigma, right? So the generic term would be like S over S square plus omega square. This is the generic term. So when you replace S with S plus sigma, right, then you get what you see over here. Okay. Understand? So this is the generic term, S over S square plus omega square. when you replace S with S plus gamma, it's a shift. It's a shift in S domain. So what is it in time domain? So let's figure that out. Let's go back to the Laplace table and check whether we can see anything similar to that. All right, so this is the table and you can see it over here. You can see it over here. S over S square plus omega square, and the inverse of that is cosine omega t. Cosine omega t. But this is not exactly what we have. What we have is S plus sigma in place of S. What do we do then? What do we do then? Can we see something on the Laplace side here where S is replaced with some S plus alpha or S minus alpha, something like that? If you check, you can see it over here. This is a Laplace transform where S is replaced with S minus alpha. Right? In place of S, every time you see S, there is something together with S, S minus alpha. In that case, the inverse Laplace is the function fs in time domain, and in front of that you have to write e to the alpha t. This whatever number which is always coming attached to S, you have to take that one and put it here as e to the alpha t. If this is minus a, it is plus a here. If it is plus a, it's going to be minus a here. So in case of inverse, you can temporarily forget about this a and treat it as fs like this, for example, right? And do the inverse Laplace, you get to the cosine. And after that, in front of that, you write e to the alpha t, if this is minus a. If this is plus a, it will be e to the minus a. Clear? Right, so this term is actually cos omega t, but S comes with minus plus sigma always. So therefore it is exponentially scaled function in time, which is e to the minus sigma t in time domain. Right, just that. And if you look at the second term over here, the second term over here, it is very similar to the first term here. Right, in Laplace table, my Laplace table doesn't have some of the inverse transforms like sine, for example. My table has cosine, but not sine. This is the sine. This is the sine. Where in the numerator, I have omega. Omega over S plus sigma square plus omega square. Inverse Laplace of this one is actually sine. Again, S is always associated with or attached with sigma. So therefore, e to the minus sigma t should precede sine omega t. This one is also sine, and e to the minus sigma t should be there because S plus sigma over here, right? But not only that, this is a product of two Laplace transforms, multiplication of two Laplace transforms. Okay, this one and this one. So therefore, this is going to be a convolution integral. So you have to integrate from 0 to, oh, sorry, we can do it as an integrator, because A is a constant, eta, omega, they're all constants. This is e to the minus sigma t sine omega t, and this is 1 over s. 1 over s in Laplace domain is actually integration in time domain. So you just simply integrate it, e to the minus sigma t sine omega t dt. Okay, right. So when you put them in the next line together, right, you will see this k1 e to the minus sigma 1 sigma t cos omega t and all the other terms like this. After that is basically simplification, right? This integration, by the way, this is not a very easy integration. Right? You have to integrate by parts. Please look up on the internet or some reference how do you integrate that kind of an expression, or in my book, it's in the appendix, how to integrate in, I think in my time, I did this in A-level, right? In A-level mathematics, we did this integration by parts. And it's a very interesting experience, if you can do that. Else, you figure it out in my appendix book. Appendix number I don't remember. Look up it. So it should be somewhere. So once you do that, you get to this expression, right? This is the whole thing. Now, to simulate this response, and obviously you can see you have cosines and sines, right? You have cosines and sines, which means oscillation. So as we expected, because of having a strong spring, right, you get more oscillations in view of a relatively weak damper. And now mathematically also we see the sines and cosines. Of course, every time you get a sine or cosine, you get e to the minus sigma t in front of that. This e to the minus sigma t means a damping, because you know sigma is coming from the damper. So damper is not zero, okay? Remember that. There is a damper. It's only weak, but it is there. So therefore, gradually the damper is going to resist the motion. If not for that, this spring will take it forever through the oscillations, right? It will oscillate back and forth, back and forth. There's no end to that, right? But now, because it is some sort of damping, this e to the minus sigma t will show mathematically that the spring oscillation is going to decay, right, gradually. Now, we started off the spring with 125 newtons, right? And then we increase it to 2,450 newtons. Now, we will keep it as it is and reduce the damper to make it a little weaker. From initial 700, now we'll bring it to 300. Okay. So with this one, we are only going to change the damper. We are keeping the same spring. So which means you are going to get the same steady state, right, as you got earlier, which is this one, because you have the same string, right? So eventually the deflection would be only 2 millimeters, right? Now when you simulate, you get something like this. The poles are at -3 plus or minus J6.3, right? They're different. -3 plus or minus J6.3. So if I draw it over here, where? Right. So now the poles are say -3 is over here. Right, -3 is over here. Maybe one of the poles is here now. The other pole is over here. This is 6 point something. This is -6 point something. Right? So you started the two poles here and here, and then you increase the spring and you brought the two poles over here. Right, critically damp the system, and now you weaken the damper and you have two poles over here and here. So every time you change the system components, you are changing the pole locations and you are going to get a different response. Now with the strong spring and the weak damper, this is the response. And if you look at the steady state, there's no change. But if you look at the look at how you get there, there's initial oscillation. This oscillation makes it a bit comfortable for you because you don't feel like you jumped on a piece of rock or on a piece of some hard surface, right? Because the surface oscillates initially and it gradually settles down. So if you ask me whether this is a good design for a shock absorber, I would still say no. Because if you look at the timeline, it's just a couple of seconds, not enough. So we need this oscillation to go like maybe some 3-4 seconds at least. And there should be some deflection over here, right? Not a very small deflection like this. So it is subjective what you really want, right? But certainly by arranging the components here and there, you should be able to do that. If you see very closely, somewhere over here, first few seconds, in fact, first 4 seconds, let's say, first 4 seconds, right? You can see this kind of oscillation. Now, next time you jump on a motorcycle, right, just check that out, how long it takes for this oscillation to die out, right? The moment you jump in, you see it goes up and down, and usually how long, how many seconds it takes, right? Right. So this is the comparison of the 3 responses. I think I already explained to you all these things. This is just a contrast by putting the 3 responses on one graph. You can see that oscillatory one, critically damped one, and the overdamped one. So overdamped one is really inefficient. Overdamped, we can also see in our society, a lot of places, government institutions, I think overdamped. Overdamped means it's very difficult to get anything to move in the system. Huge inertia, huge resistance, right? We spend a lot of time and therefore energy because the system is highly damped. It's done by the administration of all these places, okay? It is very difficult to make anything move in the systems. So we can see a lot of analogy here in control systems. If you study very well, you can relate some of these things into the society also. On the other hand, critically damped case, it is very quick. With very little energy, you move from A to B. right? This is the fastest and the safest. And the oscillatory one is fast, but it goes up and down, which means you go this way and the other way, and this way, other way, and eventually you get to the place, which is not very efficient, right? But it is better than the overdamped system. Overdamped system is the most nasty, worse. There's nothing coming from the overdamped system. Oscillatory system is a bit better than that, but it's kind of risky. Whatever you do might come at you again. And the best thing is, for many cases, critically damped condition is safe and quick and minimum energy. Okay. But that is very generic description. If you handle something very specific, you have to figure out what you really want. Don't just habitually say critically damped condition is the best for every case. No, it is not the case. Generally, yes. But if you look at a particular case plant, right, you have to figure out what should be the criteria for system design. Okay, right. So I think that's it. And final slide is this one. There you can see the pole location and the response, so that you can generalize this. If you have overdamped system, right, you have the poles like real and distinct. Real and distinct. This is the origin. These are the two poles, right? So you can see, remember I mentioned about the slow poles and the fast poles. This is a fast pole. This is a very, very slow pole. Whenever you get near to zero means zero. No movement, right? Very slow, very, very slow system. So by just looking at a pole very close to zero means it doesn't move. No action, no response, highly damped system. Then critically damped case, you have both poles working together and you are not close to zero, which means you have some good action. Oscillatory poles means complex pair of conjugate poles. First time you see they are off the horizontal line, real line, up and down, then you see the oscillations. All right, so that's it for the day. I will upload this lecture, last lecture, both to the web and also the slides, so that you can study at home. And make sure you download MatLab and you install. And not only that, once I submit, once I make these slides available, you can look at the code, right? I want you to code it yourself and troubleshoot and run it and see it for yourself, right? Any questions?
So there in the last equation, there mentions a term called phi E. What's that term?
This one. This is the phase.
All right, initial phase.
Yeah. No. Yeah. So like when you draw a sinusoidal waveform, so when you draw a sinusoidal waveform, if it goes like this is phase 0, right? But if it goes like this, there's some phase initially, and this is that phi, phase delay kind of thing. Okay, so it is the same sinusoidal waveform, but there's an initial shift on the time or angle axis or phase axis. Okay, this is time and angle, time or angle, right? So that is the initial phase. So you have frequency, phase, and amplitude, right? Any sinusoidal waveform has 3 components, right? Amplitude, frequency, and phase. And this amplitude is decaying, right? Decaying because of this minus t thing. So you start with, say, high amplitude, but you gradually decade, right? And there is a frequency and there's a phase. Initially, you start at some phase, right? So it's 5e. Look at the reference here, or look at on the internet how you can integrate this one, right? Integration e to the minus sigma t sine omega t dt, very common integration, but it goes for one whole page, A4 page, to do the integration and get to this expression. Any other questions, please? Okay, in that case, let's wind up. And I'll see you next week.